Hello, this is Gary Grider from Los Alamos National Laboratory, and I'm going to be talking to you today about how we're moving from applications uh, that are guided from architectures to applications actually guiding architectures. And why we're doing that is to transform our weapons performance calculations radically from the way they are today, and we're going to try to do that through efficiency. To remind you, Los Alamos is a nuclear weapons lab, and we take responsibility for the care stockpile, the bulk of the U.S. stockpile. And so it's a very serious, enduring mission that we have. So a little background, we've been at this a while, actually a long, long time. We were one of the first places to compute. In fact, my mentor at the laboratory actually hauled wires to ENIAC in Pennsylvania to run one of the first problems run on ENIAC. We've been computing for a really long time. Built our own system and called Maniac. Tubes, John von Neumann and Nick Metropolis did that long, long time ago. And we had the first IBM Stretch and many, many other machines along the way up until you probably remember Roadrunner, the first petaflop machine. And of course, we even have a quantum machine, the D-Wave system at the lab. And our next system is called Crossroads, and I'll be talking a little bit about that later. So first of all, I like to cover that the laboratories in the DOE complex have pretty radically different missions, different mission focuses. And of course, there's the Office of Science laboratories that do great science in the name of energy, and the weapons laboratories, Los Alamos, Livermore, Sandia, that do weapons mission. And Los Alamos, and even within the weapons mission, there's pretty radically different focuses. And anyway, I stole this format from Gary Chickapali, who's now at NVIDIA. And essentially, this graph shows the data flow complexity getting more, going to the right, and control code complexity getting more complex as you go up. And you can see that there's 4 quadrants, and one quadrant at the bottom left-hand corner is single physics and machine learning and the like, and 3D UQ lives down there. And then you've got up the upper left-hand corner, which is sort of running virtual machines and hyperscale kinds of things. And then in the bottom right-hand corner, you've got IoT or in the edge. So that's complex data flow, but not very complex control flow. And then you've got poor people that live at the upper right-hand corner that are complex in both dimensions, and that's where 3D weapons performance calculations live. And they live there because they're highly complex, multi-dimensional, multi-resolutional, multi-physics, and very, very irregular. And so those are very hard problems for computers to work on. I want to tell you a little bit about 3D UQ. You're going to hear about that and from other laboratories within the weapons complex. And 3D UQ is uncertainty quantification, and that's where we run many simpler 3D weapon simulations that are smaller, roughly about the size we ran in 2004, so about 10 terabytes of memory, and so they run on very small numbers of nodes, and of course you run thousands and thousands of those to do statistical significance studies. And that's largely what Livermore National Laboratory uses their very large computers to do. At least that's their focus for those computers. And Los Alamos is sort of at the other end of the spectrum. We run 3D weapons performance calculations for the most part, and that's our part of the complex's mission. And so you'll see that Los Alamos and Livermore buy very, very different kinds of machines, and that's why our missions are very, very different. And a question for you is how many sites would dedicate half of a premier size machine to a single problem for 7 months or a year or something like that? And we're talking about 10,000 nodes and a petabyte of DRAM for almost a year. That's a pretty seriously hard problem to solve. Apparently, it took a long time on such a big machine. And that's the kind of thing Los Alamos does every day, every week, every year. We do that all the time. So that's our bread and butter. A little bit about our current machine, Trinity. Trinity is really still current NNSA, nuclear weapons laboratory workhorse machine. It's shared between Los Alamos, Livermore, and Sandia. It's housed at Los Alamos, and it's really still quite a very large machine at 20,000 nodes and a million-ish cores. But what really makes it big is it's 2 petabytes of DRAM. It's quite large, bigger than pretty much everything else out there still, and it's almost 6 years old. Because it has such a big memory footprint, and because we run these very, very large petabyte-sized jobs, we put a 4 petabyte NAND burst buffer on it that runs at 4 terabytes a second, and it has about 100 petabytes of scratch disk file system that runs at over a terabyte a second, and then um, of course it's got the campaign store, which is where we store stuff, intermediate things that are not quite archivable yet, and of course the site-wide archive that we use as well. But that's not the only machine we have in the fleet at Los Alamos. We've got lots of machines that are there on the right upper corner. You can see the ones that are secure and the ones that are open, and I'll bring your attention to Chicoma there in the middle. It's an HPE Olympus Shasta system, about 3,000 teraflops so far. It's about to add a bunch of more nodes that are going to be A100 NVIDIA nodes, and that's a new machine, and it actually is running in nearly production mode using the Shasta software stack and Olympus hardware. So a little simple view of our computing environment. We have the Premier machine up in the left-hand corner, very, very large. Usually it will have a fairly dedicated scratch file system associated with it. And then we have all these capacity machines that you saw in that table last slide. And all those machines are up here, and they share a common set of scratch file systems and other services, NFS and Archive and Campaign and the like. And then we have these nodes over here, and these are really all about batch transfer agents. So, think if nodes or something, and their entire job in life is to move data around at multiple tens to hundreds of gigabytes a second between file systems and between Archive and Campaign and so forth. And so that's their job. Anyway, that's how our site works today. Remember that I said that Trinity had a burst buffer. Just to remind you, the system we had that before that, called Cielo, did not have a burst buffer. It just had memory, parallel file system, and archive, which is how things work for a very long time, since the mid-90s. We added the burst buffer, which was a flash tier. We also added the campaign store, which was slow disk tier, and then we had the archive. And we don't really like these tiers, but economically we have to do them because economics drives what we can afford to deploy. We really hate policy-driven tiering as well. Everybody wants to push that down our throats, and we hate that. We call that the treat everybody equally bad way of doing things. And for a site that has few users, which we do, not that many, and very, very important large runs, policy-driven just doesn't make any sense. And we feel like our campaign store is working very, very well. It's extremely reliable. It's got this tiered erasure mechanism that makes it very reliable and performs well. So we're going to try to leverage that going forward. Okay, so just to remind you, I'm going to talk now about Crossroads, and Crossroads is going to be installed here fairly soon, and we've been going through an RFP process for the last few years to get that purchased and on the way. And I just wanted to remind you the reason that Crossroads exists, and it's this weapons performance. So it's not doing 3D UQ or machine learning or AI, it's to do 3D weapons performance calculations, which might benefit from AI or other things, but largely are very, very large GC simulations. Crossroads RFP methodology, it's sort of our first step towards trying to move towards more efficiency. Of course, we have the minimum requirements of, got minimum amount of memory to do the job, maximum amount of power and cooling that we have to put it in. It's the best value for weapons performance type calculations, as I said before. There was no mention of flops in the RFP. We don't care about flops. We care about getting weapons performance calculations done. We use this thing called SSI, which is essentially many applications that represent our workloads, and even the workflows and the information about the apps that we run. And We allow the vendors to run two versions of these. One is the baseline that they can't change, and the other is the vendor may modify the mini apps in any way they would like to optimize to the architecture, as long as they're faithful to the problem being solved. We wanted to buy essentially a system that gets the most work through the system for the work that we plan to put through it with the lowest price. So that's the methodology that we use, and we're concentrating on three areas of efficiency with this machine: performance efficiency, so achieve performance on the applications, not peak performance or anything like that; measured improvement over previous platforms; workflow efficiency, which is trying to get work through the system, so that includes storage and networking and other kinds of things; and then porting efficiency. So when the vendors do make changes to those mini apps to optimize, we measure not only the optimization and what they gained from it, but we also measure the cost. How much do they have to change those applications, so that we can see what the impacts are for our overall code base, to determine how efficiency it is for the people. This is an interesting graph, a study of the outcomes from the RFP. We did two RFPs in this particular case, one called bid one and one called bid two. And each one of these is a different bidder that bid on the machine. Two of the first one and two. The second one, this is Cielo and this is Trinity. And it's essentially got three measures. It's got SSI in the blue. It's got SSI optimized. That's where the vendor got to optimize the mini applications to architectures. And then it's got peak flops. I know those aren't on the same graph, but I'm not going to compare those on the same scale, so that doesn't matter. Notice that these are all equalized to Cielo being a 1, and so at any rate, you see that there was a bid here, and the bid was didn't have very good SSI at all compared to, say, the other bid. But after they optimized, it had a fair amount of it got some gain in SSI. In this bid, very little. You had very good SSI, and what little changes they made did very little to the SSI. This architecture was GPU architecture, and this architecture was not. In the later bids, you can see a similar thing. You can see each one of these, the optimized got a little better, but not a lot. None of these were GPU bids, because everybody learned that doesn't really work very well for the problems, even if you optimize. And you can see that there's not really much correlation to flops here. How well you do may or may not be correlated to flops on the SSI. So flops didn't matter really at all from the application's point of view, and that's no big surprise. But it's just information that is interesting, I think. Crossroads will have a different storage tier system because we've learned something, and the economics have changed a bit. Campaign is working very, very well, so we're going to grow it, and the burst buffer is working very, very well, so we're going to just move to an all-flash parallel file system here in the red, and the capacity tier will grow in the purple, and then archive and factual will shrink. We're even contemplating moving the archive from HPSS to Marchive, which is basically the same technology we use for our campaign. Crossroads timeline, here it is. Mostly it starts installing in FY22, which is about a year away, less than a year away, and ends and goes production in 23. That was essentially about a year late from what we first really wanted, but that is due to the bids that the two RFP bids that we put out were separated in time. So we'll talk a little bit about the future. Really what we're after is to try to move those weapons performance calculations about 30 times faster, or get 30 times more of them through than we do today, so that we can enable human learning from those things in a far better way. So the upper part of this diagram, it shows the hopscotch or leapfrog that we play with Livermore on putting machines in, large scale machines in. You can see Trinity, Sierra, which is at Livermore today. Crossroads next, and then El Capitan is next to Livermore, and then the next one is at Los Alamos and so forth. So that's Crossroads, the machine we're talking about. And remember, of course, that the future machine, which I'll be talking about, which is the ATS slide machine. Um, this is the focus, right, for the Los Alamos machine. So that's what the machine will be deployed for. What is it trying to accomplish? It's trying to move these very, very hard problems that are complex simulations into a regime where instead of getting a single result after 7 months on half of a huge machine, maybe we get a result a week. That requires about a 30 times improvement in how to get stuff through the system. And if you look at back at the dreaded upper right-hand corner, um, complex data and complex control, essentially couple complexity and sparsity to access data and the like, we're going to have to address those problems to gain this 30x. So that's what we're going to focus on. There's two ways to go do that. One way is two ways essentially to find leverage in the industry. One way is to find leverage through hot application trends like AI and ML and the like, which is really the path that some people take. They're buying large GPU machines and hoping that they can get their applications to run well on them. We've learned um, that we can't win just by data parallelism alone, and so that technique isn't very fruitful for Los Alamos. But it turns out it's really good for Livermore because 3D UQ actually works pretty well in this regime. The other large thing that you can actually leverage in industry is tailored architectures that are manufactured by that are enabled by manufacturing trends. Things like 3D, 2.5D and 3D integration, and massive tailoring. So if you look at ARM and what Apple's done with ARM on a phone, there's like 30 or 40 tailored units within there that's tailored for the job at hand. And that's the approach that we're going to take, is to try to tailor the architectures more to our application needs, as opposed to trying to tailor our applications to the architecture that we can get. And so those are the two ways of doing things. This tends to be how Livermore is going to run their operation for the next decade or so, and this tailored architecture is how Los Alamos is going to go try to make forward progress on their problems. Anyway, there's other things out there that are also leverageable that are important too. Smart NICs, intelligence and storage, and so those two things we're also going to focus on to try to get this 30x performance improvement that we need. The machines associated with making that happen, Crossroads, of course, was sort of a first step towards efficiency, to try to at least solicit machines that are more efficient on our problems. We're also going to be announcing, and you'll see this in the next month or so, maybe you'll see it by the time you hear this presentation, a large machine that we're buying that's going to be used for AI and machine learning and simulation at Los Alamos. So it won't necessarily be used for production weapons performance, but one of its functions is interesting. It will also be a test bed for future technology for co-designing collaborations. And so we may have a midlife kicker or something like that to help us glimpse in the future. So this machine is going to be a little different than a typical classical large weapons performance oriented machine. It's going to be somewhat different for Los Alamos, but nonetheless pretty good sized, and hopefully you've heard about it by now already. Then of course there's ATS 5 and ATS 7 and larger machines that we would do, and we would hopefully do them based on what we learned from Crossroads, based on this tailoring that we're working on to try to move towards that 30x, and we'll try to demo much better efficiency with this machine and hopefully exceed the 30x by ATS 7. How are we going to do that? So today's co-design is largely taking some science, some application and algorithmic people, and some computer science abstractions people, getting them together and building, portability and portable performance layers and the like, co-designed with the application to try to make the best of the architectures that are handed to you. And what we're going to try to do is to add hardware people essentially to the co-design mix, so that co-design teams would have hardware, and changing hardware or tailoring hardware actually be fair game for these kinds of co-design teams. And so we're adding this piece to co-design at Los Alamos, and this is how we're going to do it. We're going to put teams together, and we're also going to have crosscuts for some of the parts, like the common computer science software to hardware and hardware tailors that we use. The hope is we can find a few tailoring opportunities that get us big wins for multiple applications across these co-design teams, um, and have pay NRE or R&D to have them come to fruition for our next machines. The way we're going to do that is by partnering, and so we've started a consortium called the Efficient Mission Centered Computing Consortium, EMC3, and we've got a bunch of members already. And essentially, these are like-minded technology providing organizations or like-minded using organizations, like Chevron and others that have problems that are similar to ours, and struggle with getting the kind of throughput and performance that they really need given today's architectures, and want to move forward with this tailoring efficiency concept. And so we're partnering with all these companies, and this is actually an old slide. We're partnering with more than this, to try to make that happen. The areas of interest for that organization are very, very broad, and they're essentially we're shooting for helping using these areas to help in moving towards a more efficient way to do, so that we can get that 30x that we see. Networking, of course, next generation, especially computing in the network, storage, especially computing in the network, and data movement, innovation, and the like. Resilient computing we've been into for a long time, you probably know. And then, of course, data analytics and inexact computing and other kinds of things like that. As well as, on the compute side, processor, how to tailor processing memory complex to do their jobs better. Benchmarking systems, simulation of systems that we might deploy in the future, and so forth. So that's the areas of interest for EMC3 and partnerships that we're on this page. And finally, there's a question and answer that was a question that was provided by Hyperion, and they wanted me to comment on this, and so I will. So they basically said simulation seems to be taking a back seat to the excitement around AI, yet simulation is crucial for most of the important AI, for many important AI problems. Can you comment? Well, I can't comment on if simulation is important for AI problems. I guess I would argue that there are many AI problems where simulation isn't important. Self-driving cars is more about turning sensor information into action as opposed to simulation. But I am quite sure that they're right, and that there are some applications, some simulation applications, or some AI applications where simulation is useful. But what I do see is that AI is a method that can be used to assist simulation, and that's probably how Los Alamos will use AI for the most part in the weapons program. Now, in other parts of the laboratory, biosciences or global security, other kinds of things, we'll use AI for more classical, sensors and getting information and making actionable information from non-actionable information. But I think we'll also use AI to help your simulation for the weapons program. But I think AI is cool. I think AI is cool for information science. I don't think AI is quite as cool for physics, but has its uses, and we'll try to leverage those as best we can. But I also believe that this excitement around it is drawing a lot of the industry's interest, and that makes it very hard for things that don't fall within that regime to get any air in the room. And so it's a double-edged sword for us. We'll try to make the best of it in both, where we can use it to our advantage and where we have to rail against it to get something done. we'll be doing both. And I want to thank you very much for the time, and anybody that wants to join us in our seeking backwards towards efficient computing as we had back in the 70s. Well, please contact us. These are the logos de jour at the bottom, and that's an old picture of a Ray 1 and a CDC 7600, and that person probably has bell bottoms on. Anyway, thank you very much for your time.